Can you see my screen?
Yes, sir. Yes, sir.
Okay, can I start?
Yes, you can start.
Thanks. Well, my presentation will illustrate some hybrid methodologies for solving optimization problems. In particular, we consider some optimization problems and how we can solve these problems by using a combination, some combinations of intelligent techniques. In particular, combinations between neural network and fuzzy logic, and combinations between fuzzy logic and swarm computation. The optimization issue is very important, and it is very important to underline that no universal optimization algorithm is able to solve all problems. In particular, a technique may work well on a set of problems and fail in different problem sets. In general, we can state that there is no a unique, just one algorithm which have the capability to solve all kind of problems. There is the welcome no free lunch theorem or no free lunch theorems with the plural. This theorem states that any two optimization algorithms are equivalent when their performances is averaged across all possible problems. Now we define the optimization problem in mathematical formalism. We consider a set of design variables x1, x2, xn, and these variables have to stay in an interval. This interval is defined by a lower bound and upper bound, extrema, and the goal, the aim of this problem is to find the optimal solution of the object functions, in particular minimum or maximum. If we have optimization, optimization or maximization. And this optimization is over x1, x2, xn in the interval defined by lower bound and upper bound. Moreover, we have to optimize under some constraint functions. Generally, these functions are referred with the symbol j of x, g of x, with the j which stand for the number of constraints. We can have inequality constraints or equality constraints. in particular, if we consider some optimization problems, such as the Weld beam design problem, in this case, the design problem consists of minimizing the fabrication cost of a welded beam. We can note that the objective function f of x depends on 4 variables, x1, x2, x3, and x4. Each variables is defined over a specific range, and we can note that in this example we have 7 constraint functions, in particular 7 inequality constraint function. This is an example, but we can consider other examples. For example, the cantilever beam, where we have 5 hollow blocks. The design problem is to minimize the function defined as we can see in this slide. We have 5 variables defined in the same interval, and the whole this problem is characterized by just one constraint function, j of x. In this case, it is an inequality constraint function. This is another example where we have 3 inequality constraints and 2 variables defined in the interval 0, 1. This is the example of 3-bar truss design problem where the volume of the truss structure framework has to be minimized subject to stress constraint. But for solving these kind of problems, we have the issue of complexity. The application of exhaustive search techniques for solving these kind of problems leads to huge computational costs. If the number of optimization parameters increases, the optimization problem's complexity becomes huge. This is the problem of many optimization problems, and it is very important to pay attention to computational complexity. To overcome the complexity problem, it is possible to overcome this problem, this issue, by applying some meta-heuristic approach. In particular, we consider some naturally inspired algorithm which solve the problem at low complexity. This approach, the meta-heuristic approach, is designed for solving a problem more quickly when classic methods are too slow, or for finding an approximate solution when classic methods fail to find any exact solution. The meta-heuristic algorithms may be classified in 2 categories. base models of algorithms, in other terms, the base algorithm, and variants of base algorithm. In particular, we can consider some revised versions, improved versions of the base algorithm, and these variants can useful for solving specific problems at low complexity. Base models are the first versions of algorithm, and variations are versions, revised versions that are redesigned for specific problems, or for problems, optimization problems, and compared with other optimization problems. The base model, an example of base model is the PSO, the particle swarm optimization. Of this basic algorithm, there are many variants. For example, we have discrete particle swarm optimization, fuzzy particle swarm optimization. We can note in this case that the fuzzy logic as intelligent technique is applied in this specific base algorithm. And artificial neural network particle swarm optimization, in this case, in PSO, is applied the theory of artificial neural networks to solve, say, some problems. The main issue is how to solve these problems at low costs, at low computational costs. It is possible to combine some intelligent techniques, such as fuzzy logic, neural networks, and evolutionary algorithms. It is very important to combine these techniques in a suitable manner, in a suitable way. In general, fuzzy logic is based on the observation that people make decisions based on imprecise and non-numerical information. Fuzzy sets are mathematical means of representing vagueness and imprecise information. And fuzzy logic is applied on knowledge-based systems. Neural networks are mathematical models that use learning algorithms inspired by the brain to store information. And in particular, they have the capability to learn from data. The other technique is the evolutionary algorithms. These algorithms are meta-heuristic algorithms inspired to natural phenomena. And in general, an evolutionary algorithm is a generic population-based meta-heuristic optimization algorithm. In other terms, these algorithms take into account the evolution of the population during the iteration, during the search of maximum or minimum of the objective functions. The problem is how to combine intelligent techniques. The challenge is to suitably match intelligent strategies to solve optimization problems. particular, it's possible to improve base models, base algorithms, by adding novel intelligent strategies, or by modifying hybrid techniques. Another technique, another approach is to adapt a particular algorithm to a specific problem. In this way, we adapt the algorithm according to the problem to solve. First example is an hybridization between neural network and fuzzy logic. In particular, we consider how to improve exploration and exploitation phases, where exploration and exploitation phases are two very important phases of research on space research. In a particular algorithm named Gravitational Search Algorithm, and the aim is to improve this algorithm by adding neuro-fuzzy techniques. Design suitable fuzzy inference systems is very important to improve the search performances of GSA. And in this case, we consider a combination between fuzzy logic and neural networks to improve the gravitational search algorithms in terms of performances, search performances, and convergence rate. Now I describe a resume version of GSA. GSA is based on the gravity forces between masses. The position of the masses corresponds to a solution of the problems. In other terms, the position of the masses are our variables x1, x2, xn, as seen before. And GSA in this algorithm, gravitational inertial masses, generally the masses, are evaluated by using a fitness function. This is a flowchart of gravitational search algorithm. We can note that there are some important parameters. In particular, the masses m, the acceleration a of agent or particles, and the gravitational constant g, which is a very important parameter that has to modify, to adjust during the evolution, during the iterations of algorithm. We have, as stated before, two phases, two search phases, exploration and exploitation. Exploration stands for global search. In particular, during the exploration, the algorithm tends to explore a large portion of the search space. And at the same time, during the exploration, the algorithm tends to avoid premature convergence. Whereas the exploration phase stands for local search. It is a search phase where the solution is refined. In this phase, is very important to avoid the big jumps. Moreover, it is more important to have population diversity high during the exploration and low during the exploitation. In fact, the goodness of the solutions depends on the level of diversification in the population. In particular, this level has to be high at the early stage and low at the latter stage. In particular, low level of diversification in the beginning leads to premature convergence. Moreover, the acceleration of particles has to be high during the exploration when the number of iterations is low. In other terms, at the beginning of search, and this acceleration has to be low during the exploitation phase, when we have a high iterations number. The population progress may be defined as follows. In particular, we can define the population progress as with the formula in this slide, where PP is the population progress, fit is the value of fitness function, and height is the height iteration. This is a particular definition of population diversity, but it is not one. We can have more and more different definition of this quantity. In particular, it's very important to consider the key parameters of GSA. In particular, GSA depends on force between masses, F high J, and we can note that if we start from the last equation, where is defined the acceleration of particles, we can note that and the accelerations is proportional to the total force that acts on particle, a specific particle height. But this total force depends on the force between high J particles. The force between high J particles, the first equation in this slide, depends on J of T, which is the gravitational constant. The gravitational constant depends on the parameter alpha. Now, at the beginning of the iterations, when the algorithm starts, we need high acceleration of particles. In this way, the algorithm has the capability to explore more and more space, whereas at the end of the iteration, at the end of the algorithm, we have we must have low acceleration of particles, and in this way we have a better optimizations of the problems. Now, by considering these remarks, we can design a suitable fuzzy inference system which have the capability to adjust, to turn the parameter alpha of the gravitational constant G. And the fuzzy rule defined for these fuzzy inference systems depends on the remarks, the observation before. The algorithm achieves the optimality when at low iteration, high population diversity, and high particle acceleration, whereas at high iteration, low population diversity, and low particle acceleration we must have. In this way, we can design these FIS with the two fuzzy inputs, the number of iteration and the population progress, and one output. The output is the parameter alpha, which define the value of G, the constant, gravitational constant G. Okay, this is a parameter which we adjust with the help of a FIS, a fuzzy inference systems. But there is another parameter which we have to modulate, which is the k-best. K-best is a parameter that decreases and depends by a parameter beta. This is the definition of k-best. K-best depends on the number of agents, in this case, the number of particles, and is height agent, the height particle. In the same way, we can define another FIS for the parameter beta, which is in the formula that define the parameter k-best. In this case, we consider just one fuzzy input, the number of iteration, and one output, the parameter beta. Okay, if we want to improve the performance of this algorithm, we can combine neural network with fuzzy logic. In particular, it is possible to consider a neural network which has the capability to give a value of alpha, and with this value, I have the possibility to define the range of membership functions of FIS. In particular, for our FIS, we have considered triangular, trapezoidal membership functions, but it's very important to define the range of these membership functions. To define this range, we design a suitable neural network, and this neural network gives a value alpha and n, and according to this value alpha and n, it is possible to define the range of membership functions of the output alpha. How is it possible? We can consider for this neural network 4 inputs and 1 output. The output is the value of alpha and n in this case. The 4 inputs are the iteration number, the mean of a fitness function, the acceleration of particles, and the distance between particles. But the main issue is that all these value, iteration number, mean of fitness function, particle acceleration, distance between particles, are computed during the running. In this way, we exploit the computation. To create, for creating a suitable database, and with this database, we are able to train our neural network. This is an aspect, an approach to combine suitably neural network and fuzzy logic to solve an optimization problem. The test of this approach gives very good results, and our algorithm is evaluated on two kind of benchmark functions, unimodal and multimodal. Unimodal benchmark functions contain just one global optimum and no local optima. Therefore, these test functions are used to exploitation level to assess the exploitation levels and to assess the convergence of the algorithm. And we have also the multimodal benchmark functions, which have a massive number of local optima, and therefore they are used to test the local optima, evidence, and the exploration levels. These are some examples of unimodal and multimodal functions, and we apply our algorithm, the design and algorithm on these functions, and achieves very good results, in particular very good search performance results, because we compare our algorithm, NeuroFuzzy GSA, with other competitor algorithms. Moreover, it's very important to consider the convergence rate. First of all, we need to define the convergence rate from a mathematical point of view. and the convergence rate is a ratio between NF and N. NF is the number of fitness function calculations until finding its minimum value, and N is the total number of iterations N. In particular, the meaning of this convergence rate is clear, I hope, with this slide. You can note that the lower is the convergence rate, the greater is the speed to find the optimal value. In particular, in this slide, in this graph, we can note that there is a comparison between GSA and NF GSA, and we can note that our algorithm is very good in terms of convergence rate because have a more minimum value than GSA, and our algorithm arrives first before at the optimal value with respect GSA. What are the remarks? The remarks are that the proposed neuro-fuzzy approach improves GSA in terms of optimization and convergent performances. The application of the neural network improves the results of fuzzy GSA. In other terms, NF-GSA is better than just fuzzy GSA. And the hybrid neuro-fuzzy strategy, the hybrid neuro-fuzzy combination, enhances the search capability of GSA. This is an example that shows that a good combination between neural network fuzzy logic gives very good results in terms of search performances and also convergence rate. NFGSA is an example of Bayes algorithms in a revised version. In other terms, a variant of algorithms. The other possibility is to adapt the algorithm to a specific problem. It may be useful for NP-hard problems. NP-hard problems are problems where the complexity is huge. Therefore, the other approach is to adapt a specific algorithm to a problem. In this case, we consider a specific problem named the CMCEE problem. Is the problem for composing medical crews with equity and efficiency. In general, it's very important to combine suitably component. For example, in the football, it's very important to have 11 football players, but it's very important that these players have different skills. Stands for a team feature rather than the efficiency stands for a single component feature. The problem in this case is to compose suitable team with high efficiency and diversity. This is the formal formulation of the problem, where the aim is to maximize the team with the minimum efficiency, but it's very important that all the team respect the constraints. The constraints are that if a component belongs to a team, the same components does not belong to another team. Moreover, the number of components in a team has to be the same for all the team. And the other important feature is that all the team of the solution, all the teams of solutions must have the minimum diversity. In other terms, the diversity of a team must be has to be greater than a threshold, a minimum diversity threshold. This is the problem. In this case, I underline that the problem is to maximize and non-minimize. It is a maximization problem rather than minimization problem. And we have these constraints. Now, the target is to maximize the team with minimum efficiency, with all the teams of the solution which respect the constraints. This is an NP-hard problem. This problem leads to huge computational costs. Therefore, we can apply a suitable fuzzy swarm combination to solve this problem and to avoid huge complexity. The fuzzy logic is clear, but now I illustrate the meaning of swarm algorithms. The swarm algorithms are intelligent algorithms based on the collective behavior of elements in decentralized and self-organized systems, and are population-based stochastic optimization algorithms. In our case, in the case of the problem, specific problem which now consider, we can illustrate the mode flame optimization algorithm. In general, for the swarm algorithms at each iteration, the current solutions are produced according to historical information obtained by previous generation. We consider the mode flame optimization algorithm, which is based on transverse orientations. In particular, modes tends to maintain a fixed angle with respect to the moon. This algorithm exploits the navigation method of moths around like sources. The moths fly around a spiral path, and the flames are the candidate solutions, whereas the moths positions are the problem variables. In other terms, moth positions are our x1, x2, xn of variables. The model is characterized by some equations. In particular, we can note that the trajectory of moths are a spiral trajectory, where m high k is the position of height mutant k iteration. D high k minus 1 is the distance between high moth and height flame at k minus 1 iteration. F high k minus 1 is the position of height flame at iteration k minus 1. And T is a random number. B sometimes is equal to 1. But it's very important in this kind of algorithm to find a good compromise between exploration and exploitation. In this case, we consider a novel idea, which is to split the search process in 3 phases: exploration, hybrid exploration, exploitation, and exploitation. This approach is a variant of the basic algorithm MFO. What are the variants? The variants are that during each phase, a dynamic crossover mechanism for reproducing flames is designed. Moreover, in the hybrid phase, a fitness-dependent weight factor for the moth positions calculation is introduced. And in the latter stage, a random elite flame set is designed for updating the moth positions. These 3 novelties provides a revised version of basic MFO. The dynamic crossover mechanism is based on best moth and mutant flames that are mixed through crossover for all phases, all 3 of the phases: exploration, hybrid, and exploitation. The mechanism is simple. In other terms, the height mutant flame mixes its decomponents with the height best moth H to obtain the crossover flame FCA. This mechanism is dynamic and depends on current iteration K. These are the formulas which define the dynamic crossover model. And we can note that if the crossover rate is higher, then more genetic information will be passed to the crossover flame from the mutant flame FM. Vice versa, if the crossover rate is lower, then more genetic information will be transmitted to the crossover flame from the best moth. In particular, Rj is a random number in the range 0, 1. Fm is are the mutant flames. Fc are the crossover flames. H is the best moths. Chia is the crossover rate. K is the current K is the current iteration. Big K is the max number of iterations. In the hybrid phase design, the main idea is to avoid a sharp transition between exploration and exploitation. Thus, the exploration phase must be promoted with degrading the exploration capability. In other terms, it is very important to find a good combination between the exploration and exploitation. Moreover, the other approach is to define a fitness-dependent weight factor. In this case, we consider W as a parameter that gives the ratio between the value of fitness function of the best solution, M best so far, and FMIK, that is the fitness function values of the ith moth at iteration K. This quantity, W, belongs to the interval 0, 1. Moreover, the other approach is to consider elite frames. In other terms, we consider the best moth and repeat them in the solution a certain number of times. This is an approach, but this cannot use used for all the application, for all the optimization algorithm. In fact, we will see that this approach is not applicable for our problem CMCAA. This is a flowchart of EMFO. We can note that there are exploration, exploitation, the hybrid phase, the dynamic crossover, and the mutation strategy. This revised algorithm is applied to some engineering problems. For example, the Weld beam design problem, where we can note that there are some constraints, 7 constraints, and the results shows that our algorithm is the best in comparison with the other algorithms, competitor algorithms. Moreover, our algorithm is applied to the gear train design problem, where in this case we have not constraints. Also, in this case, we have the best results in terms of search capability, search performances. The remarks are that the revised version, the improved version of MFO, mode flame optimization algorithm, improves MFO for engineering optimization problems. And our idea is to design an adapted high MFO algorithm for our problem, for the CMCAA problem. But some changes are necessary. First of all, EM4 is how to solve challenges problems with constrained and unknown search spaces. The idea is to design an adaptive version of EM4, high EM4, and remind that for each solution, an individual can belong just one team for our problems. This is very important because if we define the mod positions, but the mod positions are in the set of real numbers. whereas the team members are in the set of natural numbers. The first approach is to consider not the set of real numbers, but the set of natural numbers. Moreover, each elements of a team cannot belong to another teams. In other terms, one football player can play with a team and not with two teams. In this case, we consider, for example, a number of components equal to 100. In this case, but the value of n is a natural number. It can be 100, but are possible other values of n. Moreover, it's very important to define the best solution for preserving the elite individual information. We consider the best individual in the MOT team. In this way, we consider the backbone of a team. Because if we start for the backbone of a team, it's easy after adding other components suitable for the team. Moreover, are defined the mutant flame teams. Mutant flame teams are defined by using a random function R. This random function is important because provides a perturbation with respect to the best MOT team members, M-best. And this perturbation may be either big or small. And FMTJ is the individual of Teeth mutant flame team at the jth position in the queue. M-best is the best MOT team member set with minimal efficiency so far. L1 and L2 are random numbers in one big T. Big T, I remind that big T is the number of teams, or the number of crews. In this way, we consider two teams among the T teams. Moreover, a crossover strategy is applied, and in this case, we consider an important feature of the CMC-EE problem, our problem. In other terms, we consider the individual contribution of a single component. It's very important because, as said before, a component is important for a component, for an individual is very important, the efficiency. But is equally important the contribution that this component gives to the team. In other terms, the individual contribution depends on efficiency of individual P and their diversity with the other components of the team. Exploiting this feature, we define the crossover strategy. In particular, we consider the crossover flame team defined by of flame team or best flame team. This choice depends on the value of IC. IC, I remind that, is the individual contribution of a component in the team. Moreover, the random parameter JRAND assures that the mutant flame crew gets at least one component from the T-best MOT crew. This is very important to have just one best component to compose the team. Remind that the proposed algorithm, the revised algorithm, improved MOT flame optimization algorithm, has three search phases: exploration, hybrid, and exploitation phases. That approach, which we have described before, cannot be applied here. In other terms, it's not possible to repeat the same themes in the solution. As in other words, we cannot have two same team in a tournament. If we have a tournament, all the teams have to be not equal among them. No? Therefore, just two phases are considered, in particular, exploration and exploitation. During the global search stands for exploration, where the algorithms tend to explore all the space. This global search is accomplished by logarithm spiral. We can note that while the round function, in other terms, we must to pass from real number to natural number. For this scope, it is important to achieve this scope. It is important round the value of, in this case, the position, and to have a natural number. These explain the presence of the round operator in the definition of MTI. The MTI is the MOT crew at the time t-1 iteration, and F is the flame crew at t minus one iteration. During the local search, the refined search, in other words, during the exploitation phase, the MOT teams are updated according to their corresponding flame teams and the best flame team. The equation is shown in this slide. We can note that there are a parameter W. This parameter W is different from the previous one because in this case we have a maximization problem. with the maximization problem, we have the ratio between fmi on fm best. In other terms, fmi is the fitness function, are the fitness function values of current height mod team, and fm best is the fitness function value of the best mod team m best discovered so far. It is very important to underline that the W quantity is a quantity that belongs to the interval 0, 1. In fact, the meaning of a weight factor is that the values of W are on the interval 0, 1, and from the observation of this formula, we can note that if the current mod team is far from the best mod team, the weight W tends to 0. Whereas if W is equal to 1, the current mod crew has achieved the best fitness. But in our problem, for finding or to compose crews with efficiency and equity, it's very important to take into account the constraints. Thus, in any way, we have to introduce this constraint in the optimization. CMCA is a constrained problem. In this case, in the case where there are constrained functions, in general, constraint functions inequality or equality, the objective function has to be redefined by, it is very important to consider also the degree of constraint violation. The degree means that how much the constraint is violated. Therefore, it is necessary to define a penalty function with the definition of a penalty function. We are able to convert a constrained optimization problem into an unconstrained problem by subtracting a certain value from the objective function. One moment, it's very important, this point, because we have a maximization problem. The quantity, which depends on constraint violation, has to be subtracted from the objective function, because we have a maximization problem. In fact, we can note that the constraint violation degree is the value to subtract to the optimization, the optimal value. In other terms, the value to subtract depends on the amount of constraint violation, the degree of constraint violation present in a certain solution. We consider two basic rules, which are if the penalty is too low, then the swarm algorithm may be unable to reach the feasible region. And if the penalty is too severe, the swarm algorithm may be unable to locate solutions that lie in the boundary with the infeasible region. This slide shows as is possible to define an expanded objective function which takes into account the constraint. In other terms, big F of x is equal to fx minus rf, which is a coefficient greater than 0. And jx is the penalty function. In this specific problem, we define the penalty function as shown in this slide, where we note that for all the teams, because we have a sum from 1 to t, big T, and this penalty function depends on minimum diversity. And this minimum diversity has to be greater. All the teams in the solution have to be a greater equal diversity than the minimum diversity. And this feature has to hold for all the teams in the solution, S, referred as S in general. Now, the constraint information gives information about the constraints. Bigger value of RF conveys more information of constraints and less information of objective function. A smaller RF transmits more information of objective function and less information of constraints. These features are clear if you analyze the formulas, where we have big Fx that is equal to Fx minus Rf j of x. Remind that j of x is the penalty function, which depends on constraints. Okay, how is possible to define RF? RF can be defined as a ratio between PF, where PF is referred of the penalty factor with the value between 0 and 1, and RF is defined as the ratio between PF and 1 minus PF. This definition leads to the consideration that a lower value of PF corresponds to a lower penalty value. A higher value of PF, of the penalty factor, corresponds to a higher penalty value. Consider this definition of RF. We can rewrite the expanded function as shown in this slide. In particular, we can note that we have introduced the normalization values of objective function f of penalty function g. This why, in order to increase the robustness of our analysis, of our statistical analysis, F and G are normalized. And this is the definition of the expanded function, which takes into account the optimization value and also the effect of the constraint. Now, what is our strategy? Our strategy is to apply adaptive fuzzy penalty strategy. In this case, we apply the fuzzy logic to adjust the penalty factor. In fact, to assess how the constraints are not satisfied, an adaptive fuzzy penalty method is proposed, and the penalty factor is regulated by using population information. The other aspect is to apply the fuzzy logic to adjust the penalty factor. Also, in this case, we consider a fuzzy inference system. In particular, we design a fuzzy inference system with two fuzzy inputs and one fuzzy output. The two fuzzy inputs are the normalized values of penalty function and the normalized values of objective function. And the output is the penalty factor, referred as PF. We have FIS defined by two fuzzy inputs and one fuzzy output. In this case, rather than choosing trapezoidal and triangular membership functions, we know that from some works present in literature, it's better to define Gaussian membership function. In this case, we consider three values, low, medium, and high, for the two inputs, fuzzy inputs, and for the output. In this way, we consider these Gaussian membership functions, and once defined the shape of membership function, is very important to define the fuzzy rule. Fuzzy rules are defined by following some important remarks. In particular, the greater is the amount of constraint violation by an inflexible individual, the greater is the penalty. Vice versa, the feasible individuals have not penalty. Moreover, the penalty is relaxed according to the value of the objective function. That is, the individual with the better fitness is less penalized. Moreover, because the composition teams problem is a maximization problem, an inflexible individual with high fitness value is favored because it produces potentially better offsprings in the future generation. According to this basic rule, we are able to define the fuzzy rules Moreover, there is also the surface, and we can note that when the penalty, for example, if we analyze the rule number 3, where if the penalty is low and the value of objective function is high, this is a favorite situation. The penalty factor has to be low. Okay. Vice versa, if we consider the rule number 7, where if the penalty is high and the value of objective function is low, I remind that we are finding maximum value and no minimum value. And then the PF, the penalty factor, is high. Moreover, if we observe the rules 4, 5, and 6, where the value of penalty function is medium, when we have this situation, that is the G-norm is medium, then the value of PF of the penalty factor follows the value of F of the objective function. In fact, we can note that when in the rule 4, when G norm is medium, F norm and F norm is low, PF is defined as low. For the rule 5, we have medium, medium, and medium. For the rule 6, we have medium for G norm, high for F norm. It is a good situation because we are finding the maximum value. The P norm is high. Okay, this is these are the fuzzy rules. Now we consider our approach and the results of our approach. In other terms, we have designed an algorithm, and we have adapted this algorithm to the specific problem. In other terms, we have combined the adapted swarm algorithm and we have enhanced the approach with adding the falsification of the objective function. A very important issue is the computational complexity. It's very important because in several works, in several papers in the literature, the complexity is provided by the timing, the time running. The time running is not a good parameter to assess the complexity of an algorithm. Why? Because if we consider the time running depends on the hardware performances. And so by the specific hardware. The time running depends on programming language. Depends on also programmer skills and so on. Whereas the computational complexity has to analyze it in a strict manner, in a strict way, by using the big O notation. Because the big O notation is a mathematical notation, and this mathematical notation is very important to assess the computational complexity. In this case, the algorithm does not depend by the hardware, operating system, language programming, and so on. In our case, this is the computational complexity that seems high, but it is not high if compared when compared with the complexity of some other algorithms that solve the CMCEE problem. That our problem, the problem we have considered now. However, we consider this computational complexity as defined by the value of big T, number of Qs, the MT, the number of components for each team, the population cardinality, the total number of components N, and the discretization number of fuzzy ranges, because in order to construct the membership functions, is very important to provide the number of points that are able to give the shape of the membership function. And the big E is the iteration number. Which are the results? The results are that the fuzzy approach assures a suitable monitoring of constraints on team diversity. The swarm intelligent approach provides to the problem the feature of assuring an optimal team backbone during the generations. The binomial crossover strategy exploits the information of current individual contribution, and the evolution-based strategy affects the definition of the penalty factor during the generation. We can note that we have combined some technique to improve the results, performance results, search results, and also convergence results, convergence rate results, but it's very important to pay attention to complexity, computational complexity, because the computational complexity is a key aspect of optimization algorithms, and this computation complexity has to analyzed with the help of a big O notation that assure a strict definition of cost complexity. In conclusions, we can state that hybrid techniques are useful to solve optimization problems with huge computational complexity. Intelligent techniques can be combined with different approaches neurofuzzy or fuzzy neuro, but this is not the same because we can apply the neurofuzzy, the neural network to a fuzzy systems, or vice versa. Fuzzy theory on neural network. Moreover, the swarm algorithms can be adapted, swarm algorithms, and also other algorithms, other intelligent algorithms can be adapted to a specific problem and enhanced by using fuzzy techniques. Thanks a lot for your attention.
Okay. Thank you, Professor. Dear participants, if you have any query or any question, you can unmute yourself to ask the question.
Hello, sir. Good afternoon.
Good afternoon.
I want to ask one question. The question is, in your presentation, you have taken alpha lies as a linguistic variable in one slide, very high, high, low, and alpha can take the values. I want to it can it take the numerical values, and if it take the numerical values, and what will be the range of these values?
Okay, sometime choosing the range of a membership function in general is very important, and also the choose of the shape of membership function is important. In this case, we apply try technique. In other terms, we have to consider various different ranges, but in order to consider the best range, we apply try and error techniques, because it's very important to consider the value which came from the algorithm during the running of the algorithm, because these numbers, these values give information. These information can be used and exploited to design neural network, but also fuzzy inference systems.
Okay, thank you, sir. Thank you so much.
Thank you. You too.
Any other question from other participants? Okay, so there is no more question.
There are just thanks.
Yes.
Thanks.
Okay, so first I would like to thank you, Professor Danilo, for accepting our kind invitation and for providing us such an informative talk. So please accept our token of gratitude, appreciation, and love from the Golgotia University fraternity.
Thanks.
Thank you. Thank you.
Thanks a lot.
Thank you, sir. Thank you so much.
Thank you.
Okay. Tomorrow we have two another eminent speakers, Professor Rahman and Professor Chetty. So I am requesting all the participants to kindly join at sharply 11 p.m. Sorry, 11 a.m. for the tomorrow first session. Dr. Mizanur Rahman will be the invited speaker from the Bangladesh, and in the second session will be started at 2 p.m. In this session, Dr. Naveen Chetty will present, and he is from the Africa. So thank you for your active participation. Thank you all. If you have any query, you can ask. Okay. Thank you, everyone.